So good morning to all of you. Let us start the session. In yesterday's session, we have already started discussion with respect to uh, composition of relation. Just yeah, this is what we discussed in yesterday's session. So, what is composition of any relation R? It is just a minute. It is basically collection of all element A comma C such that A comma B belongs to R1, A comma and B comma C belongs to R2, and R1 composition R2 is collection of A comma C where A belongs to R1. Sorry, A belongs to A comma B belongs to R1 and B comma C belongs to R2. We want A comma C pair. That's it. So the relation R on relation let the R be a relation on set A. The power of R, you can take any, you can take n order of composition with itself. That is defined recursively by this R raised to 1 is R, R raised to n plus 1 is R raised to n composition on, and something like that. That's it. So looking to this, you can come out with certain composition of that relation with itself. Let me just check whether we have done or not. Yes, we have done here. R3 composition R3. So we came out with this. So this is basically called in shortcut. It is R3. I am not able to write the superscript subscript here. So just kindly bear this. It is something we just write the exponent here. That is 2. Okay. So basically it looks like something like this. It looks like this. 2 times we are doing the composition of that same relation R. So you may come out with R3 composition, R3 composition, R3 also. So if you go ahead with this, you can, no one can stop you. Unlimited composition you can carry on. So can you tell me now what will be the answer? R3 composition, R3 composition, R3. Already you are having R3 composition R3 with you. That is this. And you are composing with this. So can you tell me what will be the elements? Yeah, come on, quickly respond. What will be the R3 composition, R3 composition, R3? Hope I am audible. Kindly please respond whether I am audible or not.
Yes, sir.
Yeah, please respond now. What is R3 composition, R3 composition, R3? Already we have identified what is
So
R3
1
composition.
comma 1.
Okay, let me type 1 comma 1
and 1 comma 2.
1 comma 2.
1 comma 2.
Anything else?
No.
No, no, sir.
No. Okay. Okay. So that means we have done with this. So now in this, whether you have done this first and then you have done the composition, or whether you have done this first and then you have done the composition, is it same or right? Let us try to understand what I am talking right now. You have done this first. Okay. Now I am asking, is it same or not? Just tell me.
So it will be same.
It will be same.
Yes,
Okay.
sir.
Okay. So let us now go ahead. What we will discuss right now. We have understood now what is composition. Let me just quickly navigate here.
Hello, sir. You're not audible at all.
Oh, sorry, I forgot to unmute. Uh, Wait, I will repeat again. What I wanted to talk. I was talking like this. We already seen what is set and how we represent set. So we already learned we can exclusively state the elements of set inside the curly bracket, or we can exclusively write the property of elements belonging to that set. So something like that we already discussed like in the previous class. So this is the way we can represent the elements of set, or we can have a property that R3 is collection of all the element A comma B such that A belongs to set whatever B and B belongs to set C whatever, and A is multiple of B. This is the way we are writing the set. Similarly, how we represent the relation. So there are three ways you can represent the relation. Either you can exclusively write the elements of that relation, something like this, that we are exclusively stating what are the elements, or you may have a representation of relation in terms of matrix, where all these domain elements will be listed here in terms of rows, okay, and all the codomain element will be listed in terms of column, and the relation is from A to B, okay. The relation is from A to B. If the relation is from B to A, all the elements of B will be here, all the elements of A will be here. If the relation is from A to A, all the elements of A will be here, all the elements of A will be here, something like that. So we'll see this. So what we are discussing right now, let us try to understand how to represent the relation R1. So relation R1 can be represented exclusively by stating the elements of that relation R1, or it can be represented something like R1 is collection of all the elements A comma B such that A belongs to set B and this B belongs to set C, and whereas where the property of A comma B is what? A is less than B. This is the way, another way. Another way is what you can have the listing of all the elements of domain here and all the elements of codomain here. So basically this is relation R1 we are talking. So what are the elements of this is from B to C. So what are the elements of B? Okay, hope now it is visible. So we are just writing the elements of B here, 1, 2, 9, 10, whatever. And the elements of codomain are listed here, 3, 4, 5, 1, 2, 9. Okay. And then there is a relation from B to C. We are talking about relation R1. So this is relation R1. So if the element 1 is related to 3 in that relation R1, then the membership of 1 comma 3 belonging to R1 is 1. Membership of 1 comma 4 belonging to R1, look at this, is 1. Membership of 1 comma 5 belonging to R1 is 1. Yes, 1 indicates it is belonging. Membership of 1 comma 1 belonging to R1 is 0. It is not belonging. 1 comma 2 is belonging. 1 comma 9 is not it is belonging. Now 2 comma 3 is also belonging. 2 comma 4 is also belonging. 2 comma 5 is also belonging. 2 comma 1 is not belonging. 2 comma 2 is not belonging. 2 comma 9 is belonging. 9 comma 3 is not belonging. 9 comma 4 is not belonging. 9 comma 5 is not belonging. 9 comma 1 is not belonging. 9 comma 2 is not belonging. 9 comma 9 is not belonging. 10 comma something is at all not there. So everything is 0, 0. So please let me know if any questions with respect to this. Is it clear or not? Please let me know. This is set. This is R1 is basically a relation we are talking about here. This is B to C is having relation R1. That is what we are talking about. Is it understood or not? Please let me know in the chat box. If any questions, please let me know. Please respond quickly. We need to cover lot many things. Okay, so far if there is no question, I will proceed ahead. So this is just the way of representing the relationship. So by looking at the relationship, you can easily understand whether the relation is symmetric or not. So if it is 1 comma 3, you need to just check 3 comma 1. But basically we are checking that symmetry when you do have, if A comma B is there, then you need to check B comma A, but that element is not here at all. So this symmetric relationship normally can be visualized when you are having a relation from set to itself. We'll see this shortly. So by looking to this, you can identify all what is the cardinality of this. So you have to just count wherever is 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the cardinality of this relation, and these are the elements. That is 1 comma 3, 1 comma 4, 1 comma 5, 1 comma 2, 1 comma 9, 2 comma 3, 2 comma 4, 2 comma 5, 2 comma 9. These are the elements belonging to this relation. So there is alternative way to represent the same relation. This is just for your visual representation, nothing else. What is the alternative way to represent the relation? The alternative way is to have a graph. So in our case, we do have this is our set C, set B. Okay. So basically in terms of graph, what we do, we just have a nodes represented. This you are going to learn in your data structure subject also later on. What is graph? Graph is a data structure. So basically it is collection of all the nodes. So we are having here nodes. B is 1, 2, 3, 4. 1, 2, 3, 4. So we will have some unique elements. So what are the unique elements here? One, I will just write here. Just a minute. I will just copy this quickly and then I will do this. Oh. So I will just quickly write here the elements 1, 2, 9, 10, 3, 4, 5. One, 2, 9 is already listed, so we don't have to list again. Okay, so how we represent the relation in terms of graph. So what we do, if the element is listed as a node, if there is a relation from this element to this element, so there will be a directed edge. So there is, you can see here 1 comma 3. there is a relation, so it is represented something like this. Then 1 comma 4, this directed edge indicates there is a relation from this element to this element. 1 comma 4, then 1 comma 5, then 1 comma 2, then 1 comma 9, and then 2 comma 3, 2 comma 4, 2 comma 5, 2 comma 9. Okay, so this is the way you represent the relation R in terms of graph, and this is called as in terms of technical term, this is called as diagram. Okay, diagram of whatever that B related to VR1C. Okay, so in the graph we can easily see whether the relation is reflexive or not. So we can easily say no, the relation is not reflexive. Why relation is not reflexive? If the relation is reflexive, every node is connected to itself, self loop. So that is not there. Is the relation is symmetric? That also we can check with the graph. If there is a edge from one node to another, there has to be a edge from that node to reverse. It is not there. Is the relation is asymmetric? Asymmetric means what? For all a comma b, there should not be any b comma a in the R. So do we satisfy this? Yes or no? That we need to check. So if we say 1 comma 3, 3 comma 1, do we have? No. 1 comma 4, 4 comma 1, do we have? No. 1 comma 5, do we have 5 comma 1? No. 1 comma 9, do we have 9 comma 1? No. 2 comma 3, do we have 3 comma 2? No. 2 comma 4, 4 comma 2? No. 2 comma 5, 5 comma 2? No. 2 comma 9, 9 comma 2? No. So this relation is asymmetric. Is this relation is antisymmetric? Yes. Why? Because it is not violating the property. If a comma b and b comma c belongs to R, then a and b has to be same. If a comma b and b comma a belongs to R, then a and b whatever they are there, they are has to be same. Anti-symmetric property also satisfied. So now we need to check whether this relation is transitive or not. What does it mean? What does it mean? If you do have a comma b and b comma c, does for that pair a comma c do you have? So let us see. You do have 1 comma 3 and you do have 3 comma something. See here 1 comma 3, 3 comma nothing. 1 comma 4, 4 comma something, nothing. 1 comma 5, 5 comma something, nothing. 1 comma 2, 2 comma something. So 1 comma 2 you have one element. Now 2 comma 3 you do have. See here 1 comma 2 belongs to R. 2 comma 3 belongs to R. 1 comma 3 is also there. Now 1 comma 2 belongs to R, 2 comma 4 belongs to R, 1 comma 4 is also there. 1 comma 2 belongs to R, 2 comma 5 belongs to R, 1 comma 5 is also belonging to R, no issue. 1 comma 2 belongs to R, 2 comma 9 belongs to R, 1 comma 9 is also belonging to R. So for this 1 comma 2 there is no issue. Okay, this pair 1 comma 2 there is no issue. So let us go ahead. 1 comma 9, 9 comma something, nothing is there. 2 comma 3 is present, 3 comma something, not there. 2 comma 4, 4 comma something, not there. 2 comma 5, 5 comma something, not there. 2 comma 9 and 9 comma something, 9 comma something is not there. So yes, this is not violating any property of transitivity such that a comma b and b comma c belongs to R, but for which a comma c is not there. This property is not violated, therefore this relation is transitive. Alright, is this relation irreflexive? Yes, this relation is irreflexive because element is not related to itself, therefore it is irreflexive. That's it. So this is what I wanted to conclude, how to represent the relation. You can represent the relation R by stating the elements, or in terms of this matrix, or in terms of this graph. So let me know whether it is clear or not. If any questions, please raise your questions. I am open to all. If you have understood, kindly respond in the chat box so that I can get the feedback immediately. Do it quickly. We need to proceed ahead. I'm waiting for the feedback. Kindly quickly respond whether you have understood or not. If any questions, please let me know. Hello, I am audible. Kindly respond whether this concept is clear or not. Yes or no in the chat box. Okay. Let's proceed ahead. This we already seen how to do the union operation, intersection operation. Nothing new. No need to discuss this. This we already done. Composition of relation also we already done. Yeah. In terms of matrix, how we do the composition. So basically, what we do in composition of matrix is let me just take one simple example to understand this quickly. Let us take one simple example. Okay, so let us assume one example I will take, a short example, just a minute. Okay, simple example will take just. Okay, so let us try to understand. Let us consider this is your relation R, or in terms of matrix I just write, I don't able to write subscript. So let us say this is relation R, this is relation S, and we do want to see R composition. Yes. Okay. R composition. Yes. So let us take one example. This is having some element, something like 101, 010, 000. Okay. So we want to perform composition. So what is basically composition? You need to check A comma B here and B comma C here, and then you are taking A comma C here, something like that. So please try to understand. First of all, let us try to understand the property related to the composition. R composition S is never equal to, it is not commutative, it is not satisfying the commutative property. So S composition R, it is not satisfying the commutative property. Number two, yes, the associativity property composition is satisfying. So therefore, you do have R composition, S composition, T, let us say. So this is equivalent to R composition, S composition, T. So associativity property it satisfies, and similarly the distributive law is also satisfying. If you want to perform union operation, just a minute. Yeah. So let us say you want to perform okay, distributive law is valid for the Boolean matrix multiplication. So the composition of the relation also satisfies the distributive law. So that is, if you do have R union S and then you want to do, after this you want to do the composition with T, that is equivalent to, you do first composition, R composition T, and then you do the union operation, inner become outer and outer become inner, S composition T. So vice versa, if you do have R composition in bracket S union T, similarly you can have inner operator is union, that will become outer operator, and outer will become inner. That is what. So please remember this important characteristics of what properties this composition operation satisfies. Commutative law it do not satisfy, associativity satisfies, and distributive law also satisfies. So our task is now to just understand how we perform R composition S when the relation is represented in terms of matrix. So basically the matrix composition of relation can be found by using Boolean product of matrices. So simply what you are doing, you are just doing the Boolean product of matrices when the relation is from same set to same set. Then only you are able to do this. Means the dimension is the same and the elements are also same, then there is no issue. Okay. R is having relation from set A to B. S is also relation is from A to B. Then you are able to do this, otherwise no. Okay. So what exactly you are doing? You are just doing the matrix multiplication. 1 into 0 plus 0 into 1 plus 1 into 0. So you can see 1 into 0 plus 0 into 1 plus 1 into 0. So it is 0. Similarly 1 into 1, 0 into 1, 1 into 0. So there is at least 1. So it is basically OR operation. You are not doing 1 plus 1 plus 1 plus 1 means 2. It is 1 plus 1 means 1 or logical 1, that is 1. So it is 1. 1 into now we are talking about this third one. Okay. 1 minute. 1 into this into this into this. Then we did 1 into this into the 1 into this into this into this. Then 1 into this into this, and here also you get 1. Okay. Similarly, you carry out this matrix multiplication, you will get this composition. That's it. This is just for your understanding, nothing new. It is everything is just a simple matrix multiplication in terms of Boolean product of matrices, when the relations are represented in terms of matrix, and the operation that we are performing is composition operation between R and S. So R composition yes is this. It is simple matrix multiplication. So this topic is over. Let us go ahead. This is also we have discussed. Which we'll discuss after a few minutes. Transitive closure. This we have done. This also we have done. Yes. Now we are going to touch what is closure. Closure means what? If a relation R is not satisfying a particular property, then we will try to make that relation forcefully to satisfy that property by performing some closure operation. So, if a given relation R is not reflexive or symmetric or antisymmetric or transitive, how can we transform it into a relation R that it satisfies this property? So, for example, let us take this R. So R is equal to 1, 2, 2, 1, 2, 2, 3, 1, 3, 3. So basically you are not aware about basically R is taken from which set? Set A to B means what are the elements of A and B that are not there. So you cannot conclude whether this is reflexive or not immediately. So assuming that the elements are set A to set A, the relation R, and okay, so what I will do one thing, I will not discuss this here, I will go back to this here, closure. So let us assume set A is 1, 2, 3, 4, okay, and there is relation R1. I am just representing in terms of now matrix quickly to speed up the operation. This is your R1 from A to A, okay. So I'm just listing the elements here, 1, 2, 3, 4. Okay, so let us assume the relation is something like this. I'm just randomly writing something. Rest are 0. Let us assume. Okay, so tell me, is this relation R1 is reflexive or not? Come on, tell me quickly. Is this relation is reflexive or not? I am asking to everyone, please let me know whether this relation R1 is reflexive or not. Yes or no? Is there any difficulty for understanding? Please let me know. If you are having any doubt, please clarify. If you are remaining silent, then I am not able to understand whether whatever I am covering, it is gained at your level or not. If it is not understood, please ask me. I will repeat again. But if it is understood and if I am asking question, then I am expecting the response. So I just want to know whether this relation is reflexive or not. If it is not reflexive, then why it is not reflexive by giving counter example. Yes, Sharwari, can you unmute yourself?
Hello, sir.
Yes, tell me.
Sir, it is not because 1 minute.
Because?
Hello, sir. Because if when one one by 1,4 is there, but 4 we don't have
Wait, wait, wait,
4.
wait, wait. I will ask series of questions. When we say a relation is reflexive, yes, Sharwari, come on, continue. Hello. Yes, Sharwari, unmute yourself and respond.
So when we have 1 is to 1 and 2 is to 2 basically.
Tell me precisely when a relation R from set A to set A is reflexive in terms of the we already discussed the property for relation becoming reflexive. Tell me in terms of the precise technical term. Yeah, continue. If there is error, I will rectify you. Don't worry. Continue. Yes, Sharwari, start immediately because we are having shortage of time. We cannot wait for infinite time. I don't
So it
understand what
means
is that. Yeah.
every member is related to itself.
So, for all element small a belonging to capital A, if A comma A, that is small a comma A belongs to relation R, for every element A belongs to set A, then we say the relation is reflexive. So with respect to this, is this relation is reflexive? Yes, Sharwari, come on, continue quickly.
So no, sir.
If it is no, then give the counter example.
Uh, Sir, we don't have 2,2 and
So counter example means at least one instance which do not hold the property. That's it. So we don't have to check for another one. Though there are multiple instances, we need at least one instance which disproves the property that is meant by the counter example. So 2 belongs to set A, but 2 comma 2 do not belongs to R1. This is the way you should talk whenever you are giving the justification for a particular question. Okay. So
yes.
that's done. That's done. Great. So let us proceed ahead. This relation R is not reflexive. So by performing what operation on this relation R1, we are 100% sure that we will get the resultant transformed relation R1. So what I want, what will be that? I'm just writing this as a dash. Okay, wait, dash. R1 dash. Where is dash here? Just writing just for your understanding. This is closure. So basically, you are having subscript, superscript R. So instead of dash, there will be superscript R. So that R indicates it is reflexive closure. So what operation I should do on R1 so that I am 100% sure that whatever R1 dash that I am writing, it will be reflexive. Okay, to answer this, let me come back here. How we make relation reflexive. In general, we will change the relation as little as possible. To make the relation R reflexive, we simply add one to the set, inducing a property on a relation. Inducing a property means what? Forcefully we are applying, forcefully we are transforming a relation to satisfy that property, so that whatever the resultant relation that we get, we satisfy the property is called as a closure. So in above example, by adding that element, we get a reflexive closure. So in general, we want, in general, the reflexive closure of a relation R is on A is R union delta, where what is delta? It is collection of all A comma A such that A belongs to capital A. So what is that reflexive closure? You just perform union operation with some, you can give certain symbol. I am not able to draw the symbol here. I will just mention delta, okay? So what is delta? Delta is another set. It is collection of all the element A comma A such that A belongs to set A. Okay? So for all A belongs to set A, this is very important. It is not just A. For all A belongs to set A. I am not able to draw the symbols here. That's why I am writing in words. Otherwise, there is a symbol upside down, capital A, that can be written here. For all A belongs to A, something like here. For all A belongs to set A. This is what we have written here, A comma A. This is your delta. So when you, this is the delta option. It performs delta. What is the state that you are getting here? You are just simply getting 1 comma 3. For every element, you are just writing that A comma A. So that is your resultant delta set. So this is 1 comma 1, then 2 comma 2, then 3 comma 3, and 4 comma 4. That's it. So this is your resultant relation delta. R1 is original relation. If you just combine this union operation, if you do, you will definitely get transform version. You will get a transform version. Here it will become 1. That's it. It is just a union operation that you have done. So this is R1 now. Relation called as reflexive closure of given relation R1. So this is reflexive closure of given relation R1. We have made relation R forcefully reflexive. How we have made forcefully reflexive? By doing element A comma A such that for all A belongs to set A. We just perform union operation and we got the resultant relation reflexive. That's it. Similarly, we are able to find out symmetric closure. Similarly, we are able to find out transitive closure, but the time is limited. So we'll continue this discussion in the next session. So request everyone to post your attendance now in the chat box. Roll number followed by your name.